Good morning. In today's class, we will be looking at the orbital requirements and also examine the different orbits. To be able to do this, let us just briefly recap where we were in the last class. We told ourselves, you have the earth as it were, and you have something going round the earth, an object going round the earth. We told ourselves we would like to have the frame of reference of this on this body itself. That means I am sitting on this body as it were and looking at my rotating body. It is not that I have an inertial frame wherein I sit here and watch this, but I have what we said is a rotating frame of reference. And what did we find? If I have a rotating frame of reference, it is necessary for me to put a pseudo force, and this pseudo force we called as a pseudo or virtual force, which we called as centrifugal force. We told ourselves that this centrifugal force is equal to m omega square into r, where omega is the rotational velocity of the body as I am sitting on it, and r is the radius from the center over here, right. So far so good. The mass of this object is m. This force was required to correctly predict the motion of the body in the frame of reference of the body itself. How did this force come? Well, in the perspective of me sitting on the body is not moving, and therefore I had to put a force to correctly define the motion of the body. Namely, we said x star is the coordinate of the body, there is no change in x star, and therefore we had d2 x star by dt square was equal to 0. Using this pseudo force, we wrote an equation which we said is the earth is attracting this body due to the universal law of gravitation. We wrote it as g, mass of the body me, that is the mass of the earth if I am considering the earth, into r square is equal to the pseudo force which is acting, namely m omega square into r, and therefore we were able to get the angular velocity of rotation omega is equal to under root g me by r cubed, right. So many radians per second. This is what we did. We also went one step further, wanted to find out what is the velocity v0 of this object as it is rotating around. We told ourselves v0 is equal to r omega, and therefore the v0 is equal to g me. I have r square coming over here into it, r square, therefore it is equal to g me by r. If I express g in Newton meter square by kilogram square, mass of the earth in kilograms and r in meters, the unit we got was meter per second. This is the orbital velocity, right. Now we go one step further, ask ourselves, supposing this body is rotating, what is the period of rotation? What do you mean by a period? What is the time taken to complete one rotation? How will I say period of rotation? I find that it travels through 360 degrees or 2 pi radians, and therefore I say the period of rotation must be the distance it travels is, I have the radius r, it is 2 pi r is the total distance it travels divided by v0, therefore the distance travelled in one orbit is equal to pi d or 2 pi r divided by v0, and therefore the period of rotation will come out to be equal to 2 pi r divided by under root G me by r, and what does that give you? The period of rotation, which I call, let us call as tau, is equal to so much seconds, is equal to r is in meters. Therefore, I have 2 pi into under root, r comes on top, r square, that is r cube by G me, so many seconds is the period of one rotation. Therefore, what is it you find from this? Let's do one or two small examples. Let us find the period of rotation for two distances. Let's take two distances. Let us take the problem which we did the other day. Was when the height above the earth is 100 kilometers, we found out the value of the orbital velocity. We said it's something like 7 kilometers per second, 7.4 or something, right? I want to find out what is the period, and therefore the period in terms of seconds, tau seconds, is equal to r cubed. R cubed is equal to how much is it? We said that the radius of the earth is how much, and the height above the earth is some value. Therefore, r is equal to 6380 is the radius of the earth. Let me write it, 2 pi into radius of the earth is 6380 plus I have 100 over here, so many kilometers, into 10 to the power 3 divided by g. The value of g, gravitational constant, is 6.670 into 10 to the power minus 11, and the mass of the earth is equal to 5.974 into 10 to the power 24 kg. This is the time taken to complete one orbit, right, at a distance of 100 kilometers above us. When I calculate the value, I find this comes out to be something like 5194 seconds, or something like equal to 1.44 hours. Therefore, now I say instead of 100 kilometers, I go to an orbit. Instead of being 100 kilometers height, instead of being 100 kilometers above the earth, I go to a distance, let us say 50,000 kilometers above the earth, and now I ask what is the value of the time period. And if I do the same thing, tau at seconds at a distance of h equal to 50,000 kilometers will give me the same thing. I again put 2 pi into what I say 6380 plus 50,000 kilometers, meters, 10 to the power 3 divided by the same value again, 6.670 into 10 to the power minus 11 into, I get the mass of the earth, which is equal to 5.974 into 10 to the power 24, right. And what does this come out to be? This comes out to be something like 35.7 hours. Is it all right? All what we are doing is, we want to find the time for going through one orbit at a height of 100 kilometers. We find it something like an hour and odd, and if I have the orbit which is at a height of 50,000, it is something like 35. And if I want to plot this, let's plot it and see what we get over here. I keep this figure, I erase this part. Now I plot the radius or height above the earth as a function of time period on the surface of earth, which is something like 6,300 and something. I will get a little bit lower at a height of 100 kilometers. I got a value equal to 1.4 hours or so. Excuse me. At a height of 50,000 kilometers, I got it as equal to something like 35 or something like 35.7 or 36 hours or so. This is my period, and I have something like, the graph shows that it is r to the power 3 by 2. Therefore, the graph shows like this. Somewhere in between 1.4 hours and something like 35.7 hours, we have the value corresponding to a single rotation of the earth, and that is 24 hours. That means I have 24 hours is the period of rotation of the earth. How do you define the period of rotation? How will you define it? We define maybe when sun is vertical today and when sun is vertical the next day, that means that is the period, and that we say is 1 day or 24 hours. But actually what is happening, let's put things together. Actually when you see what is happening, you have the sun at the center of the solar system, you have the earth rotating in an elliptical fashion, and the earth is also revolving on its axis as it is rotating on this. Therefore, the solar day is going to be different, or the period of one rotation is going to be slightly less than 24 hours, and therefore because it is revolving and as it is moving, and therefore the period cannot be 24 hours, and therefore we define another one, namely we talk in terms of solar day. That means that is 24 hours period of one rotation, and we say the real actual time taken for a rotation, which we call as sidereal day, slightly less, it is something like 23 hours 56 minutes and 4.1 seconds. Therefore, whenever we say one rotation, what is happening is the earth is rotating on its axis, and as it is rotating it is also revolving, and therefore one rotation corresponds to not one solar day but one what we call as a sidereal day, which is 23 hours 56 minutes, and this works out to be something like equal to 86,164.1 second. You know, I do not think we are going to get into that depth of trying to find out the difference between a solar day and a sidereal day, and we will assume that the earth rotates once in 24 hours. And having said that, you know, somewhere in between 36 hours and 1.4 hours, we will find that you have 24 hours, and at this point what is going to happen, you know, we showed the earth over here. The earth rotates on its axis, and you have the body, when the body or the satellite moves with respect to the earth, and the rotation of the body with respect to the earth is the same. In other words, the time taken for one revolution, let us say the body is on this plane, the body is moving, let us say from east to west over here, maybe it is going round over here. The time taken for one orbit as it goes round is 1 day, which is the same rate at which the earth is rotating on its axis. In other words, the period of rotation of this body is synchronous with the rotation of the earth, and we call this orbit as geosynchronous orbit. In other words, when I have the earth rotating, earth rotates from east to west, and so also if the body rotates in a plane which also rotates once per day, we say that the rotation of this object or body or satellite is synchronous with respect to earth. We call it as geosynchronous orbit. However, if now the body is rotating on the east west axis, namely on the equatorial plane, and then what happens is it also rotates once in 24 hours, just the same way as the earth rotates in 24 hours, then any point on the surface of the earth, since the earth is also rotating once in 24 hours and this is rotating in the equatorial plane at the same rate as once in 24 hours, the satellite will always appear stationary to all points on the surface of the earth, and such an orbit is known as geostationary. We call it as geostationary because for all points on the surface of the earth the satellite appears stationary. But if by chance the orbit is not along the equatorial plane, but it is in some other latitude or some other plane, we call it simply as geosynchronous but not geostationary. Therefore, the distinction between geostationary and geosynchronous is geostationary is in the equatorial plane having a rotational period same as the rotational period of the earth, whereas geosynchronous could be at in any other plane. Having said that, it is not necessary that we should have geosynchronous and geostationary orbits only for the earth. It is possible to have the geostationary and geosynchronous orbits for any other planets so long as the planet is rotating. Any other heavenly body, if it is rotating and the satellite or object is moving at the same rate as the rotation of the body, we could have a geostationary or geosynchronous orbit. For instance, for Mars also, for Mars we could have a geosynchronous and a geostationary orbit. Any planet, any object, heavenly body which rotates, we can always have a satellite moving around it at the around it, which could be in geosynchronous or geostationary orbits. You know, all what I am trying to say is, what is the value of the height, and I call this height as radius of the geosynchronous orbit, which is equal to the radius of the earth plus the height of the orbit at which the period is going to be 24 hours. I also qualify by saying 24 hours is the solar day, and I must distinguish it from the sidereal day, which is slightly smaller, but for us, you know, it really does not matter. Maybe for a person who works on mission, he must take into consideration the sidereal day of 23 hours and maybe 56 minutes and 4.1 seconds. Therefore, let us try to put this together. We will therefore tell ourselves now, I want to find out the height of the geosynchronous orbit or geostationary orbit. And what is the difference between the two? Geostationary is in the plane of the equator, equatorial plane, whereas geostationary could be in any plane, that is the difference. Okay, we want to find out, therefore we do the same thing. Rotational period of the earth, it rotates through 360 degrees, that is 2 pi radians in 24 hours, that is 60 into 60 seconds is the angular velocity. And what is the angular velocity at a height which will be rg? That means I am considering the earth over here, I am considering the orbit going round over here, maybe on the equatorial plane as it were. I am considering this height as hg, and the radius, if I consider the radius, I say is rg. Rg is equal to radius of the earth plus the value of h corresponding to the geostationary orbit, and therefore we just had the expression for omega e. If now I were to calculate the value of the height of the orbit at which I am going to get 24 hours, what is it I get? I get g me by rg cube is under root is equal to, I get 2 pi divided by 24 into 60 into 60, and you know the value of gravitational constant is 6.670 into 10 to the power minus 11. We know the mass of the earth, and the mass of the earth we said is 5.974 into 10 to the power 24 kg, and therefore if now I find the value of rg, rg works out to be something like 42,164 kilometers. I tell myself, yes, I have the earth here, I want to find out the period of rotation or the angular velocity of rotation. The angular velocity of a rotation we derived as equal to g me by r g cube. That means we had 2 pi r, and we had derived this. In fact, we put m omega square r, which is equal to the pseudo force, and we said it is balanced by the friction, by the attraction due to the earth, and that is where we had got this expression. And therefore, we got the angular rotation of the orbit is this much, and the angular rotation of the earth, which was equal to, it goes through 360 degrees or 2 pi radians in the same time, and therefore we get the distance at which the period of rotation of the object and the period of rotation of the earth are same, as equal to 42,164. Now the height of the geosynchronous orbit is therefore equal to rg minus rg minus re, and the radius of the earth, we said that the radius of the earth is 6378 kilometers, or rather the height at which a spacecraft will appear stationary is therefore equal to 42,164 minus 6378, which is equal to 35,786 kilometers. What is it I am telling you? All what I am trying to say is, well, you have the earth, let us draw the earth and look at the rotation of the earth. You have the axis of the earth, maybe the earth as it were. The earth is rotating once in 24 hours, the angular velocity of rotation is 2 pi divided by 24 into 60 into 60, and maybe the period at which, if I have a height above the earth which is 35,000 and we say 786, is it, kilometers above, the period of rotation or the period of this orbit and the period of rotation of the earth is provided that the orbit is in the equatorial plane, and therefore this object will appear to be stationary to us. This concept was not developed by rocket engineers or people in mission, but was told by the famous science fiction author Arthur Clarke. Now Arthur Clarke has been writing a lot of science fiction books. In fact, he settled down in Ceylon, and I think he passed away several years ago, very prolific writer, and he proposed this orbit in the year around 1945, and therefore the geostationary orbit is also referred to as Clarke orbit after him. Therefore, let me just repeat this again, once again. All what we are telling ourselves is, we have the earth rotating east to west once in 24 hours, and now if I have a plane which is on the equatorial plane, and around this I have an orbit, a circular orbit which rotates once in 24 hours, the height above, the height we are talking is something like 35,786 kilometers, and at this point the rotating object will appear stationary. In fact, this was recognized, and it has been the effort to have such orbits, and the first orbit or the first geostationary satellite, that means satellite is the body which is rotating around, geostationary satellite, which was developed as a geostationary satellite, was something known as SYNCOM 2. It was launched by US in 1963, I think July 26, 1963, and that is when we had this geosynchronous satellite at that height, maybe looking at the earth always there, and that was the year when Tokyo Olympics were held, and it was the first time we had TV communication from Tokyo and people could watch it in the US and maybe in some other countries also. Therefore, this geostationary satellite is one for which the period of a single rotation is same thing as the period of rotation of the earth. Therefore, what we have done so far is we started with the velocity of orbit. We told ourselves, let us just again put down the equations clearly such that we are very clear. The velocity of the orbit V0 is equal to under root g me by r, correct. The angular rotation of the orbit is equal to g me by r omega, therefore it is equal to r cube. When we are looking at the period of rotation, when the period of rotation of the earth and this is same, we get the value of Rg as equal to 42,000, or the height above the earth as equal to something like 35,000 kilometers. And this was postulated by the science fiction author Arthur Clarke. It is also known as the Clarke orbit. Now all countries have their geostationary satellite. In India we have INSAT satellites, in all countries we have this satellite, we had ATSF and different satellites. Maybe we will take a look at these satellites, but the first one was SYNCOM in the year 1963. Having seen a geostationary orbit, let us go to some other orbits. Let's see if we can have a satellite which goes from north to south. That means this is the earth, maybe the north pole, the south pole. The satellite could go round from north to south, and there is one advantage. If a satellite can go round like this in a circular orbit, we are still talking of circular orbits. The earth, this is the east and west, earth is rotating like this, and if I have the satellite which goes round and round here, as the earth rotates, this particular satellite can see all parts of the earth. Therefore, this is known as from pole to pole, that is the north pole to south pole, this is known as polar orbit. The equations are exactly identical. Supposing I want to put it at a distance r from the center of the earth, I calculate the value of omega and I find out the period, or I calculate the value of the velocity of the orbit. Therefore, we have polar orbit, but then as it is rotating, we have the sun which is over here. Let us say the sun is over here, and what is happening, the polar orbit is really not 90 to 90, because what happens is, the earth is a little chubby, not really a sphere, and it is necessary, supposing you want the sun rays to come, that means you are talking of the center of the earth O to the center of the sun, this is one axis, and we have the orbital plane over here. If the angle between the orbital plane and the center line of the sun is kept constant, we call it as sun synchronous polar orbit. Why do we need this? If the line joining here and the polar orbit makes the same angle, the intensity of the sun which the satellite sees on the earth or any other planet will be the same, and therefore I can compare the reading of what I take today and maybe some other day, and this is known as sun synchronous polar orbit. And we have in our country Indian remote sensing satellites which keep sensing or keep looking at the earth as it were. Now let's divert our attention a little bit and ask ourselves, why all these different orbits? If I say geosynchronous orbit, that means I have the earth as it were, I have along the east west, I have at a height of 35,000. The satellite is always, or the object which is rotating is always stationary with respect to the earth, and we must do this exercise. Maybe on a clear day we go at night and we can see the satellite, we can see INSAT satellite, geostationary satellite, and when I look at it, I will see the stars and all that. We said a galaxy, stars are in a state of continuous motion. We will see the stars and other things drifting across, but this satellite will be dead stationary. That is because both are rotating at the same speed, and because it is stationary, maybe I have the INSAT satellite pointing maybe towards the center of India, maybe at Nagpur, and it is able to cover the entire Indian continent, and it is able to provide maybe communication, telephony, maybe TV programs and all that is what the INSAT satellite does. When I talk in terms of polar orbit and talk in terms of sensing the earth, why do we need this? Supposing we say some crop is grown in some part of Andhra Pradesh and I want to find out whether the crop is healthy or not, I can think in terms of, if a crop is not healthy, then it withers. The frequency what I see, or the color what I see is going to be different, I can find out from this particular satellite the nature of the crop, and I can warn the people, look here, your crop is not doing all right. Or maybe if somebody wants to catch fish or something, fish always are in the ocean when the temperatures are a little higher, maybe I monitor the temperature of the ocean and give a message to the trawler industry saying you go here and catch fish, and that is how you use the remote sensing in polar orbit, and you use, which is again, if it is sun synchronous, I will get the same illumination, I will be able to compare between the different days, and we talk therefore in terms of maybe a polar orbit and a geostationary orbit. These are the two orbits. Having said that, let us go one step further. We could as well have some other orbits. We could have a low Earth orbit around the Earth, we could have something like medium Earth orbit. In other words, I have the Earth, maybe I go to low Earth orbit, and low Earth orbit are normally used for scientific studies. You all would have scientific studies, and what are these scientific studies? Maybe in the we talked in terms of troposphere, we talked in terms of stratosphere. In the stratosphere you have the wind, we would like to find out the wind velocity. We were also told there are something like charged particles which are available in the stratosphere. Maybe I would like to measure some of these things, and that is how the low Earth orbit is used, but there is a limit to the low Earth orbit. Typically it has to be greater than 300 to 400 kilometers, otherwise the air or atmosphere which is there will cause the drag part of it. Therefore, can I assume that we should be fairly clear at this point in time relating to circular orbits about the Earth, or for that matter, why should it be Earth? If I go and have a geostationary satellite about Jupiter, it should be the same. I take the mass of Jupiter, I take the radius of Jupiter, and I can find out at what height I must have that. Therefore, I think at this point let us ask ourselves, are there any other orbits other than circular orbits? You will recall when we looked at the orbital velocities of the planets around the sun, we said all orbits are elliptical. What is the difference between a circular orbit and an elliptical orbit? In other words, instead of maybe the Earth being here, let us say a small Earth, if I say it is circular, if I say it is elliptical, maybe I am talking in terms of elliptical something like this. In other words, how do we define an ellipse? We define something like a foci, 1 and 2 foci, and you have major axis which is equal to 2a and a minor axis which is equal to 2b here. Therefore, we have, maybe we told ourselves sun is at a foci and Earth is rotating around it. Similarly, if I have the Earth here and the satellite is in elliptical orbit, I have Earth as the foci and the satellite going around this in an elliptical orbit. Therefore, you define two terminologies, namely we define something known as eccentricity of elliptic orbit which is the distance between the two foci, that means this is LC divided by the major axis which is 2a, and you find for a circular orbit LC is 0 because I have a center here and the eccentricity becomes equal to 0 for a circular orbit. There is another point which we must keep in mind, and that is the orbit need not always be east to west, this is east to west, or need not always be polar. We could have in between, maybe an orbit could be like this, maybe at an inclination. This is the orbital plane, this is the east west, I say this is the inclination theta. That means we say the angle between the orbital plane and the equatorial plane is what we call the inclination of the orbit. Let me take you through an example, and the example I quote is, see, very often we are very fortunate to be near the equator and we are not much affected, but we take a country like let us say we take a country near, let us say near Moscow, maybe Russia or something, and if we take this particular country, it is in the northern hemisphere, and if I were to have something like an equatorial orbit, he is not able to see this that distinctly, and supposing what he does is, if I have something like an elliptical orbit at an angle of something like maybe 63.4 degrees, I will come back to this a little later, and then I have an orbit which has a smaller distance here and a much longer distance here, that is the orbit is something like elliptic over here, I find that the spacecraft or the object which is rotating spends much more time in the north latitude and correspondingly smaller time in the southern latitude. And what was the second law which we said when we talked of the orbital motion? Equal areas in equal times, and that was Johannes Kepler's law, and therefore it spends much more time, and I can have in the northern hemisphere the satellite can spend something like 23 hours out of 24 hours, and this particular type of highly elliptical orbits is what the Russians call as Molniya orbit, and they operate it. It has an inclination, let me get the numbers clear, it has an inclination of something like yes, 63.4 is the inclination, the distance to the topmost point is 46,000 kilometers, and the distance from the center to the nearest point is something like only 6,800. That means you see the distance between the center of the earth and the furthest point from the earth, which is over here, and this is the furthest point away from the earth over here. The distance between the center and this point is what we call as perigee. That means this is the point which is nearest to the earth, this point is away from the earth, which we call as apogee. Therefore, in an elliptical orbit we also define something known as a perigee and apogee. Perigee is something which is the orbital distance nearest to the center of the earth, and apogee is the farthest distance from the earth. These are for the case of orbits which are elliptical. Therefore, I do not think I should go further into elliptical orbits. It is something very similar to what we study for circular orbits. We have to put a pseudo force, we have to balance it by the attractive or universal law for attraction of the object to the center of the planet, and then figure it out. But something which we have really not done is, see, we have been telling ourselves about orbital velocity. What is this orbital velocity? Let's take one more small look at it. We told ourselves we have the earth as it were. Maybe if I consider the circular orbit, I have orbital velocity v0. We also told ourselves if I plot v0, mind you we did it in the last class, and I plot r, we got the orbital velocity v0 in meters per second is equal to g me by r to the power to the square root sign, right. We find if the radius is infinite, the orbital velocity is 0. If the radius is the center of the earth, as r increases at the surface of the earth, the orbital velocity is higher and it keeps falling to 0 as we go to infinity. You know, why should the velocity of the orbit goes to 0 at infinity? How would you explain it? Is there any suggestion from you? Why should it be 0? Any thinking on it? See, we did tell ourselves, supposing the spacecraft to leave the earth, escape from the earth, well, it has to go to infinity. Therefore, when I talk of infinity, you have no attractive force on the earth, and therefore it is not in orbit anymore, and therefore you find that the orbital velocity keeps decreasing. Therefore, this tells me that the orbital velocity v0 keeps decreasing as I increase the height, because as I increase the height above the earth. Now the question coming is, from the surface of the earth you have to go to this height, which we have not yet considered. That means I require a certain velocity or potential energy to be given to go, or I have to do some work in taking a mass from the surface of the earth to go to the particular orbit at a distance, let us say r, or I have to increase the height from the surface of the earth by h. How do I figure that out? See, in other words, so far I have talked only of the orbital velocity v0. I have not told you how much velocity is required to start from the surface of the earth and go to this and then get into the orbital velocity. Therefore, let us now find out what is the total velocity required for orbiting plus taking the spacecraft from the surface of the earth or some other planet to the particular radius of the orbit. How do I do it? It is the same thing. I think if we have understood so far, we must be able to do it very readily. Let us try to do that. We want to ask ourselves, what is the total velocity which includes the orbital velocity plus the velocity required to take the object from the surface of the earth, let us say at RE, to the particular orbit at R. How do I determine it? In other words, all what I am saying is, I have the earth here, I want to take the spacecraft above the earth to a height h, and I have to insert, I have to give an orbital velocity, and then it will continue here. Therefore, what is the total velocity which I must give? How do I determine it? Again, we use the same set of equations. We talk in terms of the universal law for gravitation. We ask ourselves, what is the work required to be done to increase the height of the spacecraft, or to take the spacecraft or the object from RE to R. Let us consider the earth as it were. Now, all what I am asking is, I have the earth here, I have RE here, I want to take it from here to here through a height, let us say this final height is R and this height is h. How do I do this? What is the work required to be done? Let us say that the mass of the object or mass of the spacecraft is small m. How do I calculate the work done? In, or the potential energy required to take the spacecraft from the surface of the earth to a height h. How do I do it? Any suggestions? Yes? How will you solve this problem? I want the work which is required. And what is work? Work is equal to force into distance. What is the force? Yes, you have to get rid of the gravitational force. Therefore, let us put it together. We find that the force is equal to G, mass of the earth, mass of the body, divided by, at any radius it is r square. What is the value of the work done when it moves through a distance, let us say dr, maybe I assume that it goes maybe from a height r to a height r plus dr. What is the small work which is required to be done? dw is equal to force into the small displacement dr, and therefore the dw must be equal to g m me by r square into dr. And what is the work required as I go from maybe the surface of the earth having radius re to a height r is equal to, I just have to integrate out the total work what is required is equal to integral from the surface of the earth. But mind you, let me qualify again and again, I am illustrating with respect to the earth. I could have all these things for anybody. Supposing somebody wants to go from the surface of the moon to some height, I just have to take the mass of the moon, the radius of the moon plus the particular height what I consider. Therefore, I have G m me divided by r square into dr as I go from height. If I want to put it in terms of height, Re plus h. Is it all right? And this work must be equal to the potential energy, because you are increasing the height, therefore I have higher value of potential energy. But then we also know that there is a orbital velocity v0, that means I have some kinetic energy, and what is the total energy at a height? I have, this is the potential energy plus I have the kinetic energy, and therefore I can say that the total energy of a rotating spacecraft in orbit must be equal to, I have Re to R G m me by r square into dr plus the kinetic energy of a rotating body is equal to half m, this is the orbital velocity, and what was v0 square? We have defined it, we derived it as equal to v0 is equal to under root g me by r, please check it, and therefore I can say that the total energy in orbit is therefore equal to, let us integrate this out, mass of the thing of the object is constant, mass of the earth is constant, therefore I have g gravitational constant m me into, I have integral Re to the value of r of dr by r square plus I have half m, what is v0 square? G me by the, at that particular radius is r. Is it all right? And if I say I get started by giving a kinetic energy, that is I supply some velocity energy to this, and therefore if I say that the total velocity is Vt, this must be equal to half m into Vt square, that is the total velocity I give to the spacecraft is this, consists of potential energy plus the kinetic energy due to rotation, and therefore the total velocity what I give to the spacecraft, now I can derive the expression. Let us simplify it, m cancels over here, m is a constant, and therefore I get Vt square is equal to, let us get this here, half Vt square by 2 is equal to G me into, I have minus 1 by r, therefore this becomes what, 1 over Re, because I change the order of integration, 1 by Re minus 1 by r plus I have half G me by r. Therefore, what should be the value of Vt? Let us find out. We say r is equal to the radius of the earth plus h. Now I have something like, I find I have G me minus 1 over r plus this, therefore the right hand side I can write as equal to G me by 1 over Re minus 1 over r plus half, that is equal to minus 1 over 2 r. Please check, I may be making a mistake, please check if it is all right. All what we said is minus 1 over r plus 1 over 2 r, therefore minus 1 over 2 r is here, and therefore but r is equal to Re plus h, and therefore this gives me something like G me by 2r minus Re, that means equal to Re plus h, Re plus 2h, and I take Re outside here and I have the value of 2 over here, and therefore this is equal to Re plus h. Please make sure it is all right, and this is the total velocity Vt square divided by 2, 2 and 2 gets cancelled, and therefore the total velocity which has to be given to a spacecraft, or body when it is rotating at a height h above is given by Vt is equal to G me by Re into excuse me Re plus 2h divided by Re plus h. Now, what is it I find here? While the orbital velocity we found keeps decreasing as the height above the earth increases or the height increases, we find h is multiplied by 2, therefore, this is a stronger compared to h over here, the total velocity increases in this fashion. That means, as I go higher and higher, I need to give total velocity to the spacecraft, which is going to be much higher than the orbital velocity, and this difference is what constitutes the potential energy required. Is it all right? Therefore, I think what I do at this point is maybe I stop over here. In the next class, we will do some problems involving the potential energy, maybe the kinetic energy. We will find out the different orbits and how to solve for the orbits, right. Thank you then.